Get this thing. Poor little dude. Okay. Let's see. So I'm going to take one right out of here. Let's take one that's not too ugly yet. Find the area enclosed by y equals x squared and y equals what was it, 4x minus x squared. So they didn't give me an interval between to look at. So how do I figure out what this interval is that I'm going to use for my integral? How am I going to figure that out? Where's the intersection point? So how do I find the intersection points? So let them equal to each other. Kick ass. So they get x squared equals, so this is to find the intersection points. X squared equals 4x minus x squared. Take a minute and solve that real quick. So let's see, 2x squared minus 4x equals 0. Take out a 2x. So you get x equals 0 and 2. That's nice. It's nice and 0 and 2, they meet. So the next big thing to figure out, what's the next most important thing about this interval? I kind of went over it. So which one's going to be underneath and which is going to be on top? That's going to determine which way to subtract, right? So, I mean, obviously this is an up parabola, this is a down parabola. You can see you can do a really rough sketch in the interval that we're interested in, 0 to 2. That's 1, 1, and a 2, it goes to 4. That's amazing. Let's just do this. And then 4x minus x squared has intercepts at 0 and 4. So it's going to, and it goes through, how do I want to say this? So at 1, this is 3. Do you see that? So at 1, this is 3. So it looks like that one's going to be the one on top. This guy. So this guy is top. This guy is bottom. Hopefully that, most of the time, the down parabola is going to be on top, unless it's a really funky shape. So it makes this top, bottom, makes the thing in the middle. Okay, so you just need a rough sketch, a couple of points. To be honest, if they only intersected these 2 points, you just need one point in the middle to determine who's on top, who's on bottom. At 1, this is 3, this is 1. Okay, they do that. 3 is on top. So how do I set up this integral? It would be from what to what? 0 to 2, because that's the area that's enclosed. Who's on first? I don't know. Who goes first? Yeah, this guy. He's on top, so he's the first dude. So that when I subtract, I actually get positive answer. Minus the other dude. And then I can simplify a little bit. And now I can attack this with anti-differentiation. So do that, finish that out real quick. Is that cool? My first step there. And thankfully, one of the limits is 0. That's always nice, especially when I don't have any funky functions. It's just polynomials. So I basically ignore him. Put a 2 in, you get, bless you, 8 minus, yeah, it'd be 8 times 2/3, right?
16.
Yeah. Real quick, a whole 8 minus 2/3 of an 8 is 1/3 of an 8, so the answer is 8/3. Or just do all the shit. Is that decent? Okay, so this is sort of our first semi-application, not really. It's still just purely functions. They don't mean anything yet. But I really want to make a point of this, because this is where people kind of lose it when we get into the in-between sections that we're going to skip for a minute. These functions, this picture right here, this is the question. This is what we're finding the area of. But where is this? What the shit is this? On one level, it's like, well, that's put light terms here. But where is that function? Is it here? What does this function look like? What are its intercepts? Well, we already know that. This is basically the same function, just turn around. So what does this function look like? I'm not trying to make this more difficult. I'm just trying to point out something interesting. When you put these like terms together, you took 2 functions, combined them, made them 1. But that answer applies to, that is the area between the 2. Of course it is. Stay with me. If I graph this, what's it look like from 0 to 2? Well, that's where its x-intercepts are, right? And then it's a down parabola, so at 1, it's 4 minus 2, it's 2. So this is what this thing looks like. All right, now, again, everything we did was beautiful, perfect. You don't have to do any of the shit I'm doing right now. But just to make a point out of something that confuses people, the interval of this, the area under this function is equivalent to the area between those curves because they're algebraically equivalent, the ideas. So I reorganized this area into an area that was easier for me to get without even realizing I was doing it. Do you guys see the point I'm trying to make? Nothing wrong here. I didn't have to say anything on what I just said. But again, it's a huge point for later. I can reorganize. This is gonna give me the area, but its graphical interpretation looks nothing like the actual problems. To be honest, they only share the 0 to 2 thing, right? But I can take an area. If I had to take the area of a triangle and I kind of cut it in the right place, I could just put that there and make it a rectangle, and then it's easier to get the area. Easier. But you guys so I can reorganize it, and the area doesn't change. This is a huge idea. Integrals are areas, which very often allows me to reorganize things. 6.2 and 6.3 deal with volumes, which adds an extra level of complexity, but it's sort of the same idea. We set up an interval and you kind of lose faith in, well, what's this shit got to do with the actual problem? Well, it's a representation that shows the same volume as the original problem wanted to. Sort of like what happened here. Okay. All right. So this problem was very easy, right? Very easy problem. You with me? I'm just making a point out of this right now while it's easy about something that's going to be confusing later. So one kind of problem is you have to find the boundaries. You have to find where they cross, and that's going to set up your limits. Another kind of problem you would see in 6.1 would be where they give you the interval between which they're interested in. So something like, yeah, let's do that one. I might have assigned this, but it will. Y equals tangent x, y equals 2 sine x, negative pi over 3 to pi over 3. Now, you can't just, well, number one, you can't just start doing negative pi over 3 to pi over 3 and then do this minus this, because that I see that first. There's at least the layer of who's on top, and also, is it constantly on top across the whole interval I'm interested in? Or does it do one of these where, I'm on top of you, and we switch, right? In which case you'd have to break the interval up into two parts. Yeah, I like it. So how the hell do I figure all that shit out?
Do like the representational graph that you had before.
Sure. Yeah, I could. Sure. I could also just see where they cross and see if it's in that interval, right? So how do I see where they cross? The same way we did before. Set them equal to each other, right? Tangent x. Now how the hell do I do this?
Find what each of them are at those intervals and then compare it.
So you're ready? You're ready? When you're not sure, you rewrite things in terms of
Sine over cosine.
sine and cosine. So this will be sine x over cosine x equals 2 sine x. You are not allowed to divide both sides of an equation by something that could be 0. Does that make sense? Because you can't divide by 0. So you can't divide by something that could be 0. Could sine x be 0 on the interval I'm interested in? Yes. So I want you to realize, right now, what I could do is I could say, all right, sine x could be 0. And where does that happen? In our interval? 0. Right? And then I can just divide by it, because I've already taken care of that. I can say if sine x is 0, then that means x is 0. So let's assume x is not 0. Now I can divide by it. Or you subtract that and you factor sine x out, and then you separate the factors, which is basically what I'm doing right now, just with less steps. So if I divide by sine x, I end up 1 over cosine x equals 2, which means cosine x equals 1/2. And when is that true? Pi over 3. Yeah, further away from the x-axis. That's when cosine is smaller. So pi over 3 and negative pi over 3. So that's interesting. Do you see how that's at the end point? So those don't matter. That's where they cross, but that's the end points anyway. I like it. Now, real quick. What would tangent look like? So here's negative pi over 2, pi over 2, yeah, in there. And then pi over 3 is in there. Negative. So what does tangent look like? We'll put like 1, 2, 1, 2. What's tangent look like? Cubish. In between. Those are outside the realm anyway. So it looks like wee. And what does sine look like? And it's twice sine, so say again? Yeah, cool. I like it. So it's right here, and then it goes both ways from there. So let me do that. Just come here, you. And it's twice the amplitude of normal, right? And at pi over 2, it's going to be the maximal piece. Is everybody cool? So this is going to go pi. No, this is interesting. Yeah, that's right. Exactly. For a minute, I thought that was an interval, but no. That's one end of our interval right there, pi over 3. Right? Let me just move it over a little bit. Whee! And then the other end of our interval is at negative pi over 3. You can do this, Jeff. And then it goes down to 2 somehow. Whee! My system sucks. But now I can see from negative pi over 3 to 0, tangents on top. And from 0 to pi over 3, sine's on top. So I see where to break up my integral. So I would do a little bit of both, right? This gives you the exact stuff, and then you draw a really, obviously rough as all hell sketch. All it needs to be is rough because you know where you have to be careful from this. It gives us shit in the middle, you know where you have to be careful. All right, so how do I set up this integral then? From negative pi over 3 to pi over 3, who comes first? Tangent, because he's the one on top. I like it. So we integral tangent x minus 2 sine x dx plus, now it's going to be from what? Oh, sorry.
Yeah.
That should be up to 0.
Yeah.
Thank you. Now it starts over at 0 up to pi over 3. And now they just reverse. Is everybody cool with that? I can't allow negative areas for this specific reason because I want the area. It's not a flow rate, it's an actual physical area. In general, integrals can be negative all day long. Here I'm not letting that happen. Now try to do that. Try to figure out that interval. The only nice thing about these, we have to split it up, is whatever work you do for one is obviously the work for the other one. Just turn it around. Let me give you a little help. Whose derivative is tangent x? I don't freaking know. Right? Actually, I do, but still. It's not something we know. We don't already know that. It's not a basic derivative. So again, if you write it like this, you can do it, you can do it, you can do it. Remember now, this is 6-1, meaning all of 5 can happen, meaning section 5.5, U substitution, could happen somewhere. Just, all I did was I took this and I said, let me rewrite this, and I'm going to worry about the integral on the next step. The integral of negative sine is cosine, because 0 cosine is negative sine. Integral of sine is negative cosine. 2 just comes for the ride. And then minus, I got to still figure out this integral, I rewrote that. So of course, how am I going to use u sub on this? What's stuck somewhere? What's stuck somewhere? Can't move around. Cosine is stuck down there. I can't put cosine with dx. Do you guys see that? That's really what I mean when I say that. I can't put cosine with dx. It's 1 over cosine. Oh shit, that's ugly. But I can put sine with dx, easy. And sure enough, the derivative of cosine is related to sine. So I can see something that's stuck somewhere. That doesn't always work to look at, but most of the time it does. Whose derivative is in there also. So if I let u equal cosine, du is negative sine x dx. So all I'm missing is a negative sign, like negative, negative. So this becomes negative integral. We still got to figure out the limits. I'll do that in a minute. And then sine x dx is du. And so I get 1 over u du. All right, let me stop there for a second, because that's the relatively new stuff. If you let u equal sine, du is cosine, sure, but you don't have cosine in there. You don't. You have 1 over cosine. So you're not as free. Does everybody see what I mean? There is no cosine in there. There's 1 over cosine. So shit, I can't let u equal sine. Its derivative is not in there. But cosine's derivative is in there. Sweet. All right, now how do I change the limits? Well, u is cosine x, so when x is 0, u is, when x is 0, u is cosine of 0, 1. When x is negative pi over 3, u is cosine of that. Because you're still on the positive x side, right? Go 60 down, you're still on the positive x side. So it's going to be 1/2. The same kind of thing is going to happen on that last dude, right? You guys see that? The same stuff I just did is going to happen to that last dude. So if I kind of skip over here, I need a negative in there, so I make this plus a negative. And this is going to become the same way this did, 1 over u, du. Because I've got the same stuff here. I can just reuse it. You guys see that? That's one little thing to realize. Now I see what these are going to become. 0 becomes 1, just like it did over there. Pi over 3 becomes 1/2. I love it. Somebody out there is like, aren't there any problems that have like 2 steps? No, should have passed that by a while back. What's happening in the middle here? Let's do that real quick. 2 cosine 0, 2, minus 2 cosine negative pi over 3. We've done that enough to know that that's, have we? 1/2, is that cool? It kind of sucks when there's a minus, you got to remember. So minus 2 cosine pi over 3, again, is 1/2. So 2 times that would be, did I do the same thing here? Cosine pi over 3 is 1/2 times 2 is 1. Cosine pi over 3 is 1/2 times 2 is 1. Minus a negative, right? What do I do next? So this is plugging this in. This is plugging this in. This is plugging this in. Now it's going to be minus negative, okay, plus 2 cosine of 0 is 2. And again, the less comfortable you feel, the more you show yourself. Meaning the less you skip. All right. Plus that stuff. So now I can focus my attention on the outer stuff. So what is the integral of 1 over u?
ln absolute value.
Yeah, ln. And see how the absolute value not needed because all the inputs are positive. Is that cool? But in general, you're right.
Would it? It would.
And it's a negative sign. Yeah.
Negative.
I just want to do this first. And then natural log of, well, here's the thing. Natural log of 1 is,
0.
all right, am I trying to do too much at once? Maybe I am. So let's just put here negative natural log of u from 1/2 to 1. For 2 in the middle, right? And at the end, it's going to be natural log of u from 1 to 1/2. So see how this is going to be, the natural log of 1s are 0, and then minus and negative, so that'll be natural log of 1/2 plus natural log of 1/2. So you get 2 natural log of 1/2 plus 2, exactly. The natural log of 1/2, it doesn't matter, you can leave it like that, that's fine. Or you could make it 2 to the negative 1, bring the negative 1 down, make it negative 2 natural log of 2 plus 2, either way. But this is fine. How do you check that? Ugh. You do this, and your calculator, tell it from negative pi over 3 to 0, and then you add this much. And see if it comes out to be the same decimal as that did. Gruesome. So the steps are, if they give you an interval, you still are worried about where they cross, because it might lead to breaking the interval up. Yes?
But in the last part, wouldn't you have to set the cosine before you
No, because I changed the limits to be not for x anymore. These limits are now for you. Yeah, for you. Old Jeff, when he was taking math, when he was taking calculus, he would have had to bring the x's back. He thought he was all that, and he was like, "No, it's less work to do this, John." All right, sure. All right, so that's one of the uglier ones you would see. It's actually kind of nice when they give you a problem, you just have to find out where they cross, and there's no breaking intervals up. It's only if they give you an interval and they cross somewhere in the interval, then you got to break the interval up like we did here. Okay. All right, so let's do section 6.5. Now let me can I bring that with me? I worked out a little example something, but of course I probably left it in my office. Oh well, too bad for me. Let me see if I can remember it. Yes, it was a relative easy one. That's right. What's the area of this triangle? Yeah, because it's 1/2 the base times the height, so you get 5. Do you see how, if I ask you what the average height of the triangle is, let me say that again, because this is a very strange question. Over the length of how long the triangle exists, what's the average height? What do you think? 1. And if you look at it, if you, poor little dude. Here's 1. If you cut it right here, can't I take that and fill that in? Flip! And then make a rectangle. This is sort of like that reorganization of the area we were talking about earlier. So the general idea this is approaching is, this would be something like, here's a function, and I want to know the area below it. Well, that would just be the area of this triangle. But then really what I want to know is the average value of the function itself over that range, which is equivalent to the average height, because what's the function it will give you? Heights. I know that all that sink in. So if you really think about it, all I did, so what was the average height? It was 1, because if I take the area divided by how long the area is. In fact, think about this. If I take the area divided by the length, I'm going to end up with the width of the equivalent rectangle. Now, is it only a triangle you could do that with? No. A really simple example. No, don't freak out. The actual work we're going to do is going to be stupid easy, but let me just go concept on you for a little while. So for example, if I had this is almost too easy of one. I mean, if I had, the sine function, what is the average height of the sine function? Well, that's 0, because I could kind of I could take this and fill this in, it comes out to be 0. But I can take any function really, wow, and there's got to be somewhere, some height where if you cut it and you could fill this in, you can get an equivalent rectangle, right? So the average height here would actually be probably up here, because maybe you can cut this guy off and fill that in, cut this guy off and fill that in. I mean, we're not actually going to be doing that, thankfully. That's the visual behind the work we're going to do. All we're going to do is, if I get the area divided by the length, of course I'm going to get the width of the equivalent rectangle, and that width would be the average height. Please let that make sense, because I wish it was explained to me like that. Back in young Jeff's early days of math. That's all this is doing. And so this is almost too easy to believe. That's why I wanted to do this one first. Sort of like making layups before you play basketball. The average value of a function over an interval b to a, let's do it actually, a to b, there you go, buddy, is find the area I'm talking about, and then divided by the length. Of course you're going to be left with the width of the equivalent rectangle, which would be the average height of that function. Let's do an example. So you don't have to do this, but if I give myself a little sketch, 1, 2, 3, 1 over x squared, so that's 1 at 1, 1/4 at 2, 1/9 at 3. This thing really decreases quickly. So I'd guess the average height to be somewhere below a half. You guys kind of see that? I mean, it doesn't matter if your guess is way the shit off, but it depends on how good your little sketch is. But it's not a bad idea to do a rough sketch. It's the average height across this interval. It decreases pretty fast. Should be kind of on the lower side. But how do I do this? I just do this. What area, total area am I talking about? Be the interval from 1 to 3. That's crazy. Of 1 over x squared dx divided by 2. I like it. 3 minus 1. So here's a really silly example I just came up with. I'm not anywhere near being a farmer, but let's say I have this big area and I'm putting manure out. I'm going to plant something, this manure out. And some places it kind of heaps up, and some places it goes like that. What's the average height of manure? Well, I just figure out the amount of manure divided by the area I'm dealing with, and that's one more dimension than we're dealing with here. I mean, but that's a relatively simple idea, and that is equivalent to just evening it all out. Hopefully, not with my arm, but oh well. Right? And then just seeing how tall the damn thing is, right? It's really what we're doing here in one dimension, which is awesome. So what do you get for the interval of this? So let's see, that's x to the negative 2. When you integrate it, the power goes. When you differentiate, the power goes down. When you integrate, the power goes up. So this should become x to the negative 1 divided by that new power. Is that cool? Yeah, when you get the negative powers, your brain kind of balks on the idea of up and down. I totally can relate to that. And then you just plug those in. You get negative 1/3 minus negative, so plus 1. 1 minus a third is 2/3, divided by 2 is 1/3. So 1/3 was a decent, I mean, my little less than half guess, obviously that's 0.33. Yeah, it's a pretty good guess. Okay, I like it. So it's a really nice example of how this work we do, how it relates to some physical manipulation, some geometric, just thinking about what we're doing. What is it doing? I don't have to actually do any of that shit I was talking about, thank God. That would get a little freaky. Let me chop this off from this X to... No, we have to do that. That's effectively what this is doing. I like it. So let me do this. I'm going to talk a little bit about what we're about to get into, and then we'll take a break. And we'll come back and we'll get into it. Unfortunately, I could not find my... I don't know where the hell it is now. I haven't seen it in a while. I told you about that thing. You open it up, and it just kind of flares open. It's such a beautiful visual, and I'm like, it's been a while since I taught 180, so I haven't used it in a while. But it's basically shaped, I could find a YouTube video maybe, shaped like this, so it's compressed. When you open it, it's just got all these doily looking things, but you open it becomes a sphere, right? So if I rotate this shape, Cheshire cat smile, if I rotate that shape around the x-axis, well, the shape I've got is going to probably become some kind of ellipsoid, right? I guess. But if I did a better circle, you're not going to do it, Jeff, so just stop. Pretend like that's half of a circle. If I rotate it, I'm going to get a sphere. So the disconnect we have as students sometimes is the integral we end up with. You cannot directly relate what you see in it necessarily to what it is we're doing. Just like earlier. Now, to be honest, it starts off really nice. Let me see. Oh, that's right, I could do that. Let's go ahead and take a break, because I want to pull up a few animations to show you so that you don't have to suffer through my horrible drawing. So let's come back at 2.